ELF3. So, before, again, like what we did just now, we ran the second ELF. We're going to run the third ELF so that we can see what it does, right? So if you open a Linux shell here, right, I want you guys to run third. And you shouldn't see any output in your terminal. You should see an output in your present working directory. Does everyone see me when I'm turtle? Does everyone see turtle.jpg appear inside their folder? So this program writes an image file to our disk. The question now is, where does this image file come from? These are the sort of questions that you try and answer during reverse engineering, right? Because when you see a program does something, you need to know how the program does it, right? Because if an image file gets dropped onto your folder, maybe it's downloading the image file, maybe the image file is hidden somewhere and then it pulls it out, right? There has to be some mechanism whereby it gets the image file and then puts the image file onto your computer. And knowing how it does that is important. Okay, think about what the implication is if you have a computer virus that pulls files from the internet versus one which has its files baked into it, right? If it pulls the files from the internet and you are a system admin, then you can block the files from being downloaded from the internet. But if it is baked into the program on the computer already, you cannot block it with a firewall. Does that make sense? Make sense to everyone? Okay. So when we do initial analysis, right? We're gonna do this again. You go back to your Ghidra project window, right? And then everyone should know how to import programs by now. You drag and drop the third binary, right? And then you open it, should launch, and you allow it to auto-analyze. Analyze, right? Let's continue first. So same thing, click on the pink main function on the left. You should see the main function decompilation output on the right. Now I want you guys to tell me what are the global variables that we can see in this function. There are 3. Okay, red code is 1. Turtle dat is another, and turtle dat len, right? How do we know they're globals? They are blue, right? So again, if we double click any of them, it will jump inside the disassembly view to show us what these globals are, right? Inside the program space. Okay, other things to take note of. We see our friend memcopy one more time, right? Then what are the 3 other, okay, I mean there's malloc and there's free being called. What are the 3 other functions that are being called for main? You can just read it out. RC4 init, RC4 crypt, and save. No, I asked you for save instead of free. Okay, then is there anything suspicious about the naming convention for these? What does it sound like? Crypto. Crypto what? Encryption. Yes. So maybe there's encryption being used inside here, right? If we step into the save function, you will see more familiar strings that we're expecting. We see the file name that gets written, turtle.jpg. We see the functions fopen, fwrite, and fclose. Can anyone tell me what the F in this case stands for? File, right? So we're doing file operations. We're opening the file turtle.jpg. We're writing to the file turtle.jpg with length turtle.len, and then we're closing the file once we're done. Right? This is the Pythonic equivalent would just be open, write, close, right? Same thing. Okay, so that's our first pass, right? So the globals, right? turtle.dat, turtle.len, and red code. And something that's important that you guys can also notice. So I want you guys to double click on red code, and it should bring you to the disassembly view here, right? I want you to notice this section called xref. Can anyone tell me what xref might stand for? Cross-reference. What's a cross-reference? Xref over here, xref means cross-reference, okay? Which means in other parts of a program, it might be referencing this variable. So it's like if you have a Python source script, right? And then you are referencing some global, it will tell you every place where the global is being used. So for example, and some of them is labeled as W, and some of them is labeled as R. Any guesses what W and R are? Write and read. Yeah, so if we go to red code, right, over here tells you where it gets written to, and over here tells you where it gets read to. Over here tells you where it gets written to, and over here tells you where it gets read to. So this, what is the purpose of looking at cross references, right? So for example, we're starting with main. Let me go over to save real quick, and then turtle.jpg. So turtle.jpg is a global string inside this program. Then I want you to notice what the cross references are. The cross reference tells us that turtle.jpg is used in the save function. It's not used in the main function. On the other hand, this string, me when I'm turtles, is used in the main function, and you see if I double click, it'll jump me to where it's being used, right? But it's not being used in the save function. So cross references tells us where data, tells us where functions or other addresses are being used in other places in the binary. Is everyone clear on this? If we go back to red code, the global red code, what function is it being used in? Main. How many times is it being used in main? 4 times, right? And this corresponds with what we see inside the decomp. Red code is being set here once, red code is being set here again, red code is being read over here, right? So this is a write, this is the first write, this is a read at the very end, this is another read, this one is, oh, it's just part of this block as well. So they've doubled it up. So every time something is being written to and being read, right, it will tell us. And this is useful because, like, let's say you start with a string, then you don't know where the string is being used. You know the string exists somewhere, but you don't know what function is using it. The xrefs will tell you, right? Okay, next thing, viewing data, right? So we have a very large global here, which is turtles_dat. So if you go over to turtle_dat, inside the Ghidra disassembly view, you should see a very small minus sign to collapse. So you can collapse this. Right, you can open and collapse it. I want everyone to collapse it. Reason being, turtle_dat is very big. If we look at the numbers here tell us the offset of the data. And you notice, usually it's incremental. We go from 5B to 5C to 5D to 5E to 5F, right? Here we're starting at 104060, and then we jump all the way to 104963. That is a gap of about 50,000. So there's about 50,000 bytes inside turtle_dat. Does everyone, does this compute? Yeah. Either way, you should be able to see all of this here, right? And remember just now what we did, right? We select the whole thing, then we Control-C, copy as Python byte string or whatever, right? But copying a 50,000 byte buffer is not usually wise, right? Computers don't really like that. And if you copy and paste that into a Python script, it'll probably it'll throw a hissy fit as well, right? So instead, let's analyze the binary in another way that we should be familiar with by now. What I want everyone to do is to go to Window in the top bar and then Bytes. If you go to Window and then Bytes, it should produce a hex dump, which looks a lot like what we saw in HXD. Now, for most of you guys, right, once you open this, you will only see the hex dump itself. It should only look like this. So if you want to see the ASCII representation, right, the characters that these are representing, is you click the small wrench up there, top right, and then you make sure cars and hex are both ticked off. So I want everyone to do this. So yeah, so what happens now? We now have a hex dump of the bytes that we are looking at. So when we're at any position, right, and then we highlight it, the resultant bytes will get highlighted inside our Ghidra byte view as well. So another thing that I want you guys to think about, right? We know that this program drops a JPEG file, right? We know what the JPEG file magic looks like. Does anyone remember what a common JPEG file magic is? EAFF, JFIF is also another one, JFIF, right? Either way, if you look up here, right, there is no discernible file magic. This whole section just looks like random data, right? And This lines up with something that we brought up earlier. If you go back to the main function, right, we saw RC4 crypt. So what we're looking at is probably encrypted data, right, which is another form of obfuscation. So the JPEG image of the turtle has been encrypted, and we can't view it unless we decrypt it. Does everyone agree with this? Okay. And this was what we brought up earlier, what functions are interesting. We saw RC4 init and RC4 crypt. So can anyone do a quick Google search what RC4 is? So you can see it says here RC4 is a symmetric stream cipher. You don't need to know what symmetric nor stream means in this case, right? You just need to know that RC4 is an encryption algorithm. And if you remember how encryption algorithms work, they take in some data, they take in some secret key, and then with that secret key, it produces encrypted output. Then that encrypted output, you use the same secret key and you'll get back the original data. This one clear for everyone? Lock and key, right? And RC4 is one of many cryptographic functions you may encounter, right? Other cryptographic functions that are very common in malware include AES, Cha-Cha or Salsa20, right? Common enough that we can bring it up, right? And Blowfish, not on the slides, but that's another encryption algorithm that's commonly used. So we don't need to know too much about how these encryption algorithms work. What we need to be able to do is to recognize them. Because then if we can recognize the encryption algorithm, we can find someone else who has already written a decryption algorithm for it and then use it. So let's try decrypting RC4, right? So we can use CyberChef to help us with RC4 decryption, but we need the RC4 key. So just looking at the decompilation here, right? Is there anything which stands out to us? Okay, I want you guys to do, okay, the RC4 key is expected to be 16 bytes long. Let us take a look at the first line of code that's relevant, right? Memcopy. What does memcopy do? Copy memory, right? So we're copying 16 bytes of the data, me when I'm turtles, into the variable loco28. So this is some string. This is some string. I'm going to rename it to some string. Then notice that some string is being passed into RC4 init. Anyone know what init means? What init is short for? Initialize, right? So this string, this 16 character string, me when I'm turtles, is being passed into the initialization for RC4. What could this imply? Yeah, it implies that this string, this 16 byte string, might be our 16 byte key that we're using for RC4, especially because we don't see any other instances whereby data, 16 byte long data is being shifted around for our RC4 use. Does this make sense to everyone? So you see, we didn't say that like from the start, or there's no variable name that says, yeah, me when I'm turtles is the key for RC4. But we can intuit it out. We can use our intuition, we can use our powers of analysis to figure it out. Because if we know RC4 takes 16 bytes as its key, and we see in initialization that it takes this variable, which happens to be 16 bytes long, and happens to have a interesting string that's 16 bytes long being written to it, then maybe that interesting string is our key. Okay, so what's the key? Yeah, you just look at it, me when I'm turtles, that's the key. So next thing that we need to do is we need to extract the turtle data, right? So remember what I said just now, when we are trying to copy data, usually what we would do is we would just select the thing, then right click, copy special, whatever. But this is 50 kilobytes of data, right? You don't want to copy a 50 kilobyte buffer into your clipboard. So instead, we will programmatically pull it out. So remember that these are just bytes, right? Like turtle.dat is just bytes somewhere inside the program. So that means we can read it. We can read the program and just look really hard, and then we can pull it out. Does it make sense to everyone? No. Okay. Think of it this way. Let's imagine that the program is one really long source script, right? Like you can just imagine this as one really long source script. Then if I want to take a specific part of the script out, I would just scroll down until I see it, right? Like traditionally. We're going to do that same thing conceptually. So we're going to go like inside Python later, we're going to go from the very start of the program And we're going to scroll all the way down until we get to the position where turtle data is. So it's like going from all the way up here, then all the way down until just start around like here or something, yeah, here. We're going to go all the way to here, and then we're going to start extracting the data out. Does that make sense now? Everyone should have extract.py inside the folder as well, right? So extract.py, what this does in Python, it opens a file, and then it will do what I just said. It will go to a specific position inside the file. It will treat the program as just a normal file. Then go to a specific position there. Then it will read out the bytes of the encrypted image, and then it will dump it out for us. Does this make sense? Yeah. But for us to dump it out, we need to know the position that we're dumping from and how many bytes that we're going to dump out. Because if not, you're just like, hey, find the image for me. How is it supposed to know where the image is or how big the image is, right? So this is the part where we go back to Ghidra and take some information from there. This is the start of the bytes, and this is the end of the bytes. So what is the size? If you know the start and the end, end minus start, right? So the end is 10F963. Let me go back to here. So 10F963. So that's the end. Then what's the start? The start is 104060. So end minus start, 104060. Very important when you're doing this in Python, right? Make sure got 0x in front. If not the Okay, so we've managed to find the size of the image. But the way that we find the position of the image to start dumping out from, right? I want you guys to take your mouse, and then I want you to just put your mouse over the number here. You just hover over it, and a small little box should come out. When that little box comes out, right, you should see this text that says byte source offset. Does everyone see byte source offset? Okay, that value, that number tells you the position of the bytes inside the program. So what position does it tell us? What does it mean if it's plus 3060H? The H means it's an hexadecimal. So it's not 3060. It's 0x3060. Does this make sense to everyone? Yeah, so a bit of a trick there. Right? So byte source offset is plus 3060 in hex. Yeah. So if everyone has managed to see 3060 just now, right? Plus 3060, right? So that means our data offset 0x3060. So this should fill in the rest of the script for you guys, right? Okay. So everyone should now be able to run extract.py with these parameters that we filled in. And you should get turtle underscore enc coming out. Yeah, so in CyberChef, right, you can take turtle enc and drag and drop it as the input. It should look like this. You should just see a bunch of garbled data there, right? That's because that's the encrypted data. Then what encryption algorithm are we using to decrypt it? Say again. RC4. And what did we determine the password or the key to be from the decompilation? Me when I'm turtle. So I'm going to copy that wholesale just to make sure it's correct. Me when I'm turtles. And then you paste the passphrase in. And then now you can see the output is a lot more familiar. We can see JFIF, which is the file magic for JPEG. And then if you just press the magic button, because CyberChef got magic button, you see it will render the image, and it's the image that we expect, me when I'm turtle. So yes, summary for this section, right? What did we learn from this ELF file? We learned how to identify encrypted data, how to identify its position, its size, right? How to dump it out, and then identify encryption algorithm. So we managed to identify as RC4, right? And then knowing that it's RC4, we could use existing implementations of RC4. We found the key, and then we could decrypt the encrypted data and get our turtle image back. You see? Okay. So this is the implication here. What we are working with now is a toy program, right? The program just gives you the turtle image. Imagine it's a computer virus. Then by your logic, I just run it, then the thing will come out. No, you shouldn't just run it. By doing this, we're able to extract data outside of a program without having to run the program. Yeah. Because if the program is dangerous, you don't want to run it. If you find a safe way to get the data out, then just do it the safe way lah, right? Does that make sense? Yes. So actually, your rationale is not completely wrong, right? In very advanced analysis, sometimes you really do just run the program, but in a very safe sandbox environment. So you run it in a safe environment, and then using more analysis tools, you're able to pluck out the decrypted version from memory. But this is more straightforward and safer and doesn't involve running it. Okay. But yes, that's a good point, and that's part of the point that we try to drive home with data obfuscation, right? Most data obfuscation can be defeated by just running it, but when you're dealing with malware, you don't run it.